going to record any side conversations you're having. All right. What? It's recording right now, by the way. Anyway, so right here, this is an equation to figure out how much energy is gained or lost, basically, or how much heat. The Q is the amount of heat supplied or lost. So if you took a piece of iron and started heating it up, you could calculate the amount of heat it absorbed. Or if you took a piece of iron and put it in the freezer, you could figure out how much heat it lost. M is the mass. And C, this one might be a little new to you. C is the respective substance's specific heat. Mr. Furlow, what's specific heat? Oh, I'm glad you asked. Specific heat is the amount of energy that something needs to change temperature. So, for example, if I have something and its specific heat is 1, then it takes 1 joule of energy to raise 1 gram of the substance 1 degree Celsius, okay, or 1 degree Kelvin. And then delta T is the change in temperature. And change, the delta, the triangle there means change. And change is always going to be final minus initial, okay? And that's important because in this case, we're going from 30 degrees to 40 degrees. We're warming it up. We're heating it. So we have a positive change in temperature. If instead we were measuring the change in temperature of something we put in the freezer, the temperature would be going down and we would have a negative number here, indicating that we lost energy. All right, so in the question on the exit ticket, they give you information similar to this. It is not the same numbers. And you have to find the specific heat. Once you find the specific heat, you can look at your reference tables, and there's a little table that has some common elements and their specific heats. Specific heat is fairly unique. So if you know something has a specific heat, like aluminum, is 0.897. So if you calculate that the specific heat of your mystery substance is 0.897, there's a good chance it's aluminum. Okay. Anyway, in this instance, we take our, and I got a mistake right here. That should be 20.8. All right. So then we're going to say 20.8 equals 6 grams times C times a change in temperature of 10 degrees. I don't know what C is, so I'm going to combine my 6 and my 10. That's 60. Then I'm going to divide both sides by 60, and that gets me over here to 20.8 divided by 60 equals C. That comes out to be 0.35. So we could look at a, let's see if I can find specific heat list. I don't know if this will have it on here. There's 3.5. Yeah, no. Well, copper is 0.385. I don't know. This is what happens when you make up numbers. They may work, they may not. But that would be the specific heat. That's how you do it. And the tricky part, because we haven't practiced this, would be you've got to realize you need this equation, which the equation is also on your reference tables. There's a list of equations and symbols. Okay, so the equation is there, but once you have the equation, you just plug in the numbers and solve for whatever's missing. Okay, you've been doing that since what, 8th grade, 7th grade? This kind of thing we've been doing. You've done CK12s on this. You've done worksheets with this. So we have the equation: 1 mole of zinc plus 2 moles of hydrochloric acid produce 1 mole of zinc chloride plus 1 mole of hydrogen gas. All right. If you are given 10 grams of zinc and you need to know how much hydrogen is produced, because maybe you have a hydrogen powered car, I don't know, then the first thing you have to do is find the molar mass of zinc and convert from grams to moles. Then you use the mole ratio from the equation, which is in this case a 1-to-1, and you convert to moles of hydrogen. Once you have moles of hydrogen, you use the molar mass from the periodic table to calculate the number of grams in the number of hydrogen moles, and that comes out to be 0.15 grams. Questions? Okay. Just know you've got, in this case, you're converting from grams to moles of zinc to moles of hydrogen to grams of hydrogen. All right. If I want a reaction to take place, now I can just put the reactants together and hope it happens. And some things will happen very quickly and very easily. Some things do not. So we could also heat up this thing. So we could add some fire here. I think I'm drawing my fire backwards. I don't know why, but it is. Anyway. So we're going to heat that up. Now, what happens to molecules when they heat up? How do they move slower or faster? Faster. By the way, I'm recording. It's just recording audio, but just so you are aware. And so if they move faster, are they going to be more likely or less likely to bump into each other? More likely, right? Just like if I told you guys, I'm not telling you to do this, but if I said get up and walk around the room, you know, you might bump into each other, but probably not. If I ask you to run as fast as you can all around the room, you'd be more likely to bump into each other, right? Okay? And so with reactants, every time they react, there's a chance the reaction can take place. And if you heat them up, they move faster and they hit with more energy, and they're more likely to react. So, in short, heating the reactant speeds up the reaction because there are more collision between the molecules. Okay? Okay. Acids like lemon juice taste sour. Okay? You know, the last 10, 20 years, they've been making more and more sour candy, which has always boggled my brain because I'm like, candy is supposed to be sweet, not sour. But whatever. You guys do you. I'm old, all right?
Your opinion sometimes.
Why?
Because what? Candy can be sweet and sour. It's not only
No.
sweet. And it's still, but it's not like, it's not a sour that's not supposed to be for candy, you know? It's like a, you know, never mind. I just don't like that.
What she's
Me-
trying to say is that candy doesn't like always have to be sweet. It can explore other
And
tastes.
sour candy
Yeah.
isn't like an invariable sour.
Okay, let me clarify something. I am not talking about, say, like lemon drops, which are like lemon flavored and they're a little sour. Okay? I'm talking about those things like warheads and to a certain extent sour power straws, although I don't mind them all that much. But like the really sour stuff where the only point is to be sour. Like what?
I feel like that's just a sign of you getting old, Mr. Grillo.
Well, I said that.
No old people like sour candy. Okay.
Okay. Anyway, yeah, YouTube's gonna love this. Anyway, so acids are sour. The reason that sour power straws, sour candy is sour is they add citric acid to it. Okay, this is the same reason lemons and oranges are a little sour. Okay, they're a little sour because they have citric acid in them. They're nowhere near as sour as a lemon. Yeah. Anyway, acids also turn blue. There's two types of litmus paper. There's blue and there's red. So if you take a blue and a red, let's see what I can do here. All right. So here's my beaker of acid. Right. If I take and I have I have a piece of blue litmus and I put it in there, it's going to stay blue. If I have a piece of red litmus, that's wrong. I did that wrong. Hold on. I have blue litmus and red litmus would stay the same. Blue litmus would turn red. Okay, in the acid.
What's a litmus?
Oh, litmus paper. It's little strips of paper and they're coated in an indicator so that when they come in contact with an acid or a base, they change color. They're kind of outdated, but this always comes up. Because nowadays we have strips that you dip it in and they're all the same strip and it turns, you know, this range of colors if it's an acid, this range of colors if it's a base. If you have a fish tank and you ever check the pH, it's kind of like that. But anyway, so blue litmus turns red if it's an acid, okay? With a base, okay, don't ask me why my beaker is red, I don't know. If you put blue litmus paper in there, it just stays blue. But if you put red litmus paper in there, the red litmus paper turns blue. Okay? And let's see if I can. So that's litmus paper. Well, actually, that's indicator paper. That's not actual litmus paper. There's two different. That's litmus paper. If the picture will load. Anyway, this one right here, if you can see the cursor on the screen, that's it. Get back here. All right, so and bases taste bitter. Think about soap. Have you ever accidentally gotten soap in your mouth, washing your face or something? It tasted bitter. They're slippery. Think about soap. It's slippery. If you're doing laundry and you get some bleach on your hands, it feels slippery. Even when you're trying to wash it off, it still feels slippery. It's because it's a base. Bleach is a particularly strong base. Red litmus paper turns blue, and this is what I remember. I like to keep things simple, right? And when I was a kid, it was hard to remember, well, is it blue that turns red or red that turns blue? All right, but I figured out, if I remember that bases turn blue, they can't turn blue if they're already blue. So if bases turn blue, then it must be red litmus that turns blue in a base. And if red turns blue in a base, then blue must turn red in an acid. So I remember this, and because I remember this, then I know this. I can figure that out if I have to. All right, questions? Sure. All right, I'm actually going to redraw this. All right, let's say we have an atom, okay? And we have an electron here and it moves up to there, right? Is it moving up the energy levels or down? It's moving up, right? What if I have one here and it does that? Moving up. What if I have one here and it does this? Hmm? Yeah, it's still moving up. Good. Okay. Because there's a diagram like this, and one of the arrows is like this, where it points down, and I was concerned that that would confuse people. Okay. Now, these electrons, did they gain energy or lose energy? They gained energy. And because they gained energy, they got excited. So we say they're in the excited state. Right? But then, eventually, they're going to fall back down to where they came from. And when that happens, are they gaining or losing energy? Right, they're losing energy, and then that energy is given off as what?
Little squiggly lines.
Yes, that's the technical term. As light. I think it was you may said it. So they give off light. Now it may not always be visible light, but they give off the energy. So gaining energy, they move up to higher energy levels, and when they lose the energy, they move back down. That's why your toys glow in the dark. If you've ever had a glow in the dark toy or sticker or something, and you held it up to the light, and then you took it into the bathroom with the light turned over, you're like, oh, it glows in the dark. Okay? You know, when you're little, right? Or maybe now, I don't know. But that's what was happening. When you held it up to the light, all the electrons were moving up to higher energy levels. And then they're falling back down. And they're moving up, and they're falling down and moving up. When you take it into the dark, they stop moving up because they're no longer gaining energy, but they're still falling down slowly, right? And so it glows in the dark. And if you leave it in the dark long enough, it stops glowing, right? That's because all the electrons have gotten back to their ground state. All right. If we have an ionic substance, it dissociates and forms ions. Because it has ions in it, we call this an electrolyte solution. Okay? Electrolytes conduct electricity. If we take a covalent substance, like sugar, right, it does not dissociate. It does not form ions. Right? So when you take a crystal of sugar, one little grain of sugar, and you put it in your tea or coffee or whatever, it disperses. But there's still whole molecules. These split up and form ions. But sugar is going to stay as C6H12O6. C6H12O6. You're just going to have these whole molecules floating around. And that's why they taste sweet. Right? So that's a non-electrolyte. It does not conduct electricity. Right? So if you had an unknown sample, okay, and you know that it is a non-electrolyte, do you think it's ionic or covalent? It's probably covalent. And if you had sample 2 and you knew that it was an electrolyte, it would probably be ionic. Isn't it ionic? Alright, so Mendeleev, when he was making his periodic table, honestly, he was just trying to figure, as I understand it, it's not like I'm that old, but as I understand it, he was really just trying to figure out how to arrange them to put them in a textbook for his students. Okay? And he said, all right, So if I start over here with the lowest mass, then I have a metal, then I have a metal, then I have metal, then I have a non-metal, non-metal. Wait, I got another metal. Well, it's stupid to put it there, so I'm going to put it over here. Metal, 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 non-metal, non-metal. Wait, now I got another metal. No, I'm going to put it over here. Metal, metal, non-metal, non-metal, and so forth and so on. And so what he did, when he realized that there was a pattern, is the breaks from one row to the next row were based on chemical properties. And that's still true today, because we have metal, metalloid, non-metal, metal, metalloid, non-metal. And at the end of each period, we have a non-metal, and at the start of the next period, we have a metal. So what makes one row stop and the next row start is chemical properties. Okay? Okay. Aha. Yo. All right. So I think that is it. Do we have any questions?
No. Ooh, class is missed. Let's go. Sorry.
Memo to self. Send recording to her parents.
No!